Okay, so we finished off sequences, and then the next logical place to go from that is series. Take a bunch of terms, and now we add them all up. So this is going to be 4.3, infinite series, which we'll start today. We won't finish today. Okay, so just remember the notation, right? This is hopefully not new, that if we say n equals k to infinity, we sum up an. That means we're doing ak plus 1 plus, and we keep adding up all of these terms. Okay, and what we're interested in is when indeed we have infinitely many of these terms, and again, just like always, we need some concept of convergence. What does this mean for, how can we make sense of adding up an infinite number of things and calling that just some finite number? So we want to define convergence, and of course we don't want to reinvent the wheel from scratch. We want to use the kinds of concepts that we know about convergence as sequences. So we want to define convergence, but making use of what we know about sequences. Okay, what we know about convergence of sequences, and then we'll get some of our convergence results basically for free if we can do that. So what that means is I need to take this question, does this series converge? And what I need to do is rewrite it as a sequence somehow and ask, does that sequence converge? That's what I want to do. So I guess there's a natural way to do that, is to say, well, we could take a sequence that consists of, the first term is just ak. The second term is ak plus 1. That's a number. ak plus 1, ak plus 2. That's a number. And we can generate a sequence like this by just adding one more term onto it each time. And these are called partial sums. So we're going to define these partial sums. Okay, so I'm going to call it S sub n. S sub n means I'm adding up all the terms up to an. So ak plus 1 all the way up to a sub n. Okay, and n here is just some finite number. So n might be 18, maybe k is 1. This means I'm just adding up 18 real numbers, and I'm going to get a real number. There's no concern about whether this blows up or anything. This is just a number. So these are all numbers. Each of these is a finite sum. Right, and we can work it out exactly. And then we look at this as a sequence. Okay, so the sequence now becomes these partial sums. And that's great. Again, we know lots about sequences. We know how to define convergence. We know some tests for convergence. And all that is going to come in very useful for series. So right away, we get a definition of convergence of a series like this. We're going to say this series converges as long as this sequence of of partial sums converges. So there's our definition. So we say that this guy converges okay, and we're going to also give it a value, right? We add up these infinite number of terms, and we want to somehow say this adds up to some number. So we're going to say this converges to the number a if the sequence of partial sums converges to that number. Okay, of partial sums. Sn converges, right, with the limit of these things equal to a. This is a reasonable definition. Any questions on that? Okay, so we'll work with that. And then, of course, if this sequence of partial sums diverges, we'll say that the series diverges. So if the sequence Sn diverges, the series diverges. Okay, so we have convergence and we have divergence. Okay, and already we know some ways to test this. And even better, we know some ways potentially to test this without needing to guess at this number a, right? Because we know how to do that for sequences. So we'll do a couple examples. Let's look at this series. N equals 1 to infinity of 1 over n plus 1. So here I'm just going to do a little simplification. Take note of the fact that we can rewrite this thing. We can do partial fractions on this to try to simplify it so that we just have one of these terms in each of the denominators. So if we do partial fractions, we're going to get this is 1 over n minus 1 over n plus 1. Okay, and then we need to look at the partial sums, because the partial sums are going to tell us whether this series converges. Okay, so here are the partial sums. We'll write down a few of them. Okay, so S1, we just write down the first term, the n equals 1 term. So that's 1 minus a half. Okay. Partial sum number 2. We write down, okay, the first term plus the next term. So we're going to have 1 minus a half plus the n equals 2 term. That's a half minus a third. Okay, we hopefully start to see the pattern here, right? I've deliberately not simplified these things, but if we do one more term, we get 1 minus a half, half minus a third, okay, and then the n equals 3 term. So n equals 3, that's a third minus a quarter. Right, and all of these terms, we're getting a lot of cancellation going on. Minus half plus half. All these inside terms are canceling out. So this is really 1 minus a third. This is really 1 minus a quarter. Right, and if we keep going, we should expect that in general we get this cancellation continuing to happen. 1 minus, 1 over, and this is n plus 1. And of course, you can prove that. How would you prove that? Induction, yeah. I'm not going to do it, but you could verify this by induction. Okay, so this is our sequence of partial sums that we have to look at, Sn. Now we happen to know the general form of the nth term. And our question is, do these partial sums converge? So does Sn converge? And what say you? Yeah, it does, right? There's no trick to this. So now we're looking at these terms as n goes to infinity. And what we have is that the limit as n goes to infinity of Sn is simply equal to 1. Right? So the partial sums converge to 1. And that's the way we defined the series converging, right? So just from this definition here, we know that since the partial sums converge to 1, the series converges to 1. So we're going to say that indeed n equals 1 to infinity of this, 1 over n plus 1, converges to 1. Questions? Okay, on the other hand, we could have something like this. So something like this, of say minus 1 to the n. Okay, and we get, okay, s1 equals minus 1. s2 equals minus 1 plus 1, that's 0. Right, s3 equals minus 1 plus 1 minus 1, that's minus 1 again. S4 equals 0, and so on, right? And it's going to keep alternating between minus 1 and 0. And the general term is going to be minus 1 if n is odd, and 0 if n is even. Okay, so here we've written down our partial sums. We get something that doesn't converge, right? It's bounded, but it just keeps oscillating. So we're going to say this series doesn't converge because the partial sums don't converge. So since Sn does not converge, we're going to say this series also does not converge. This diverges. Okay, so again, we had this example. This example was simple. I could write the terms in a simple form where there was obvious cancellation, and we could work out exactly what this limit was with no work whatsoever. But of course, we know in real life it's not going to be like that, and we need other conditions. So one of the first conditions that we had for these sequences, for deciding if a sequence converges, right, we had different things. We said we could use the definition of convergence, the tests that we had, or we could check that if it's a Koshi sequence. Koshi sequences always converge, and the good news is they don't require us to guess at the value of the limit. Okay, so since convergence of series is nothing other than convergence of a particular sequence, we can also write down a Koshi criterion for this. Okay, so we want to apply our Koshi criterion. So to apply the Koshi criterion, okay, for convergence, what do we need to look at? We need to look at, again, the partial sums, and we need to look at two different terms in the partial sum sequence, right? Not neighboring terms, but just arbitrary terms that are sufficiently far along the sequence. So we need to look at, okay, some m greater than n that's sufficiently large. Okay, and consider Sm minus Sn. Okay, so what is this going to simplify to? This is S1 plus S2 plus Sn plus Sn plus 1 plus Sm, right? So I assumed m is bigger than n. minus S1 plus S2 all the way down to Sn. I should call these A's, I guess. Let's call these A's. Where's my eraser? A. Okay, and again, there's some simplification that happens here, right? Because a lot of these terms are the same. A1 appears, and then it gets subtracted off. A2 appears, it gets subtracted off, all the way down to AN. AN appears, and then it gets subtracted off. So what we're really left with is AN plus 1 plus AN plus 2, all the way down to AM. Okay, so what this really means, if we come back to our series, the terms are A1, A2, A3, ... What we need to be able to do is say that as long as n is big enough, I can pick any group of terms, any group of a bunch of consecutive terms, however many of them I like, that are next to each other, and add them up. And we should be able to keep this less than epsilon, right? As long as this n and this m are big enough. Right? Because that's what our Coshy criterion said. Our Coshy criterion said pick a tolerance, epsilon, however small you like. There should be an n star out there, such as long as m and n are both bigger than n star, this difference can be made less than epsilon. All that means is that, again, I can take a whole bunch of neighboring terms. As long as I start far enough out, I can take as many as I like, add them up, and it's guaranteed to be less than epsilon. And that makes sense. It's sort of like saying, my series is well approximated by going A1, A2 to AN. And if I start adding up terms that I've left off, it shouldn't add too much to it, right? If the series is converging, then once I've added up enough terms, I should get close to the right result. Terms that I've left off should give a small result. So this is my definition, or my theorem, which we'll call the Cauchy criterion for series. Okay, so we're going to say that a series converges Okay, we're not going to give the value here. We're not going to try to guess at the value here. Again, this is an equivalence. If and only if, for every epsilon greater than 0, there exists an n star, such that if n and m are bigger than m star, then if I add up all the terms between an and am, it should be small. So an plus 1 plus am is less than epsilon. You can even say m bigger than or equal to n if you want. It's not important here whether I start at an or an plus 1. That's not important. What is important is to say that I can pick as many terms as I like as long as I start far enough out, add them up, and that sum is going to be small. These leftover terms are small. This result makes sense? You believe this? Okay, so let's see what we can do with this result. We'll go back to the same example that we just did. N equals 1 to infinity, 1 over n plus 1. And we happen to know that an is 1 over n minus 1 over n plus 1. Okay, and now we want to check the Cauchy criterion. So to check the Cauchy criterion, we need to choose some epsilon bigger than 0. It's always the first line. Okay, and then we need to pick an m and an n. Right? Our goal is to find an n star. We're not sure yet how big these have to be. That's what we need to work out. But we'll start with picking some m and n. One of them's bigger than the other one. Doesn't really matter which one. And we want to add up all the terms in between them. So we look at the terms that in between them. We go an plus 1 all the way down to am. So these are not our partial sums anymore. These are just leftover terms. Okay, and what does that look like? We get 1 over n minus 1 over n plus 1. 1 over n plus 1 minus 1 over n plus 2. All the way down to 1 over m minus 1 over m plus 1. Okay, again, there's lots of cancellation, right? This negative term will always cancel with the next positive term, all the way down to here. So we're left with 1 over n minus 1 over m plus 1. And I'm safe here to drop the absolute values, right? Because we know that m plus 1 is bigger than n. We started with that as an assumption. And that means 1 over n plus 1 is going to be less than 1 over n. So this is positive the way I wrote it. Now this is our usual case when we're playing with limits and definition of limits and things like that. We need to force this to be less than epsilon, right? We just need inequalities. We need inequalities that are going the correct direction, right? So I'm allowed to do anything that keeps the inequality going that direction. It doesn't have to be tight, right? I don't have to make any of this exact, as long as I'm keeping things going the right direction. The other thing we know from working with the Koshi criterion is that it's annoying when you have both n and m floating around. It's much easier to just work with one of them. So it's nice if we can drop one of them. Here, the easiest way to drop one of them is to say, here I have 1 over n, and then I'm subtracting something positive. This would get bigger if I just ignored the second term. Again, this standard practice when we're trying to work with this Koshi criterion is see if there's a way we can eliminate one of these terms, one of the either n or m, because it's annoying having both of them around. And now we're probably in a place where we can try to set this less than epsilon. Right? Indeed, we can force that to be true as long as n is big enough. So this is true if n is bigger than 1 over epsilon. So we're going to call this our n star. And as long as n is bigger than epsilon, m is also automatically bigger than this same n star. Right, so this is our Cauchy criterion in action. Is a simple example to work through, but it has the very nice advantage that we never had to guess at the value of the limit, which can be very hard to guess at in real-world cases. So here we're going to say, okay, great. That means the series converges. Okay, we don't know the value that it converges to, but it has a definite limit. And again, as long as you know that it has a definite limit, you're in business to start doing some approximations, to start adding up some of the partial sums and knowing that a finite number of terms, as long as you take enough of them, should start getting you close to the result. Yes?
Should we be particular about n star being a natural number? Or does it really matter?
Should we be particular about n star being a natural number? It's not that big a deal, right? You can always round it, up to the next natural number. But no, I wouldn't fuss about that too much. Unless you're in a very delicate technical problem where all of a sudden this starts to matter, that you have something that you've set equal to n star and it has to be a natural number. But no, in general, as long as these things are big enough, you're good. Okay, so we can also use this to show that a series diverges, right? We know that for Cauchy series, for the Cauchy criterion, there was an if and only if statement, right? The sequence of partial sums converges if and only if it forms a Cauchy sequence, right? So if it's not a Cauchy sequence, we automatically know it diverges. Those two things are completely equivalent. So if we do this example, say cosine n pi over 2, and we want to show that this diverges. Okay, so in this case, we want to show that the Cauchy criterion breaks. So that means there should be some epsilon out there such that no matter how big I choose n star, I can always find an m and an n such that I add those terms up and they don't get small. Okay, so we're going to say we can pick any n star that we like, right, no matter how large it is. I could pick this to be a googolplex if you like, right? And it's still not going to be enough to make these terms add up to something small all the time. The other thing that I use, I don't need to show that something is going to break for all possible choices of n and m. I just need to find one case where it breaks. If I can find one case where it breaks, then the whole definition falls apart. So we just need to make one clever choice of n and m that are bigger than this. So we need one sort of clever choice of n and m that are bigger than n star. So here, I'm going to pick them looking at sort of the structure of this. For example, I know that if n happens to be a multiple of 4, right, I'm going to get cosine of some multiple of 2 pi in here. That's going to add up be 1. So I'm going to just pick n to be some multiple of 4. So let's choose n to be, OK, some multiple of 4. How about 4 n star? That's certainly bigger than n star. And that's going to give me a term that's not small, right? That's going to make this equal to 1. And then we're in business. So I'll take, say, m equal to n plus 1. I wouldn't want to go to n plus 2, because then all of a sudden I'm going to subtract that 1 back off again. Okay, so if we look at an plus an plus 1, this is going to be cosine of 2 pi n star plus cosine of 2 pi n star plus pi over 2. Okay, this adds up to 1. And it always adds up to 1. It doesn't matter how big my n star is, right? You can take n star as enormous as you like. Take n star equal to the number of fundamental particles in the universe. I don't care, right? This adds up to 1. And 1 is not less than any epsilon I can choose. So if I pick this to be my epsilon, for example, what have I done? I found an epsilon that breaks this. It says, choose this epsilon. No matter how big you pick your n star, I can find a way to force this sum to stay bigger than or equal to epsilon, right? That means this is not a Cauchy series. Okay, so here we're going to say that the Cauchy criterion failed on us. Okay, and the Cauchy criterion, again, that theorem was an if and only if theorem. It says that if we're not a Cauchy series, we're not a convergent series. So right away we can say this series diverges. Any questions on this example? It always feels more complicated trying to break the definitions than trying to satisfy them, I think. But we can sort of learn a principle here. What let me break the definition? I was able to break the definition because I found this term in here, right? And even with really big values of n, I could always find this term that was equal to 1. Or in other words, I could find a term that wasn't getting small. And that was really the thing that let me break this. So this is a corollary of our Cauchy criterion. Right. The corollary is just sort of a little mini theorem that kind of follows immediately off of a bigger theorem. And this says, really, the reason we could break this is because these terms were not converging to 0. So if we happen to have, I'll write it like this. Suppose that this series converges, okay? Then automatically we know that the limit as n goes to infinity of these terms has to go to 0, right? If they don't go to 0, if we have terms that keep trying to get big again, then we can always do this and break convergence. So another way to say this is, or if the limit of this does not go to 0, right? Either it goes to something other than 0 or it just doesn't converge, then the series diverges. Right? This statement and this statement are exactly the same statement, just in different words. Okay, so this is a test for divergence. I give you a series, and you look at the terms in here and say, wait a minute, but this doesn't converge to 0 as n goes to infinity. Then you're done. You know you have a divergent series. Okay, so this we can use as a test for divergence. What about the other way around? If I have a series and I happen to check that this works, what can I conclude? Nothing, right? So again, it's always important to know in your theorems which ways the implication go. Okay, when we were talking about Cauchy criterion and convergence, the implication went both ways. It was an if and only if. In this case, the implication goes one way. If this is true, then this is true. If this is true, that doesn't tell us anything. So it's important to be careful with that, right? We knew this from looking at the harmonic series, for example, when we added up all those 1 over n terms. That was a divergent series, even though the terms themselves got small. Okay, so this is a good test. We want to, again, learn things that we can learn from other problems that we've solved. We know, we've kind of seen before, there's a link between adding up series and doing integrals, right? Okay, that's not so surprising because doing an integral, when we defined the integral, we basically defined it using not infinite series, but using finite series and then taking limits. That's not surprising. And we did one example, actually, where we were trying to work out the convergence of an integral, and we related it back to a series. So it's natural to try to learn what we can about convergence of series from what we know about the convergence of integrals. One thing we know about integrals is that if we're looking at an indefinite integral, it's a lot easier to decide if it converges if the function is positive, right? Then we had nice tests, comparison tests, whatever. we knew things like if we had a positive function and we integrated it a longer way, the value of the integral will go up because you're just adding more positive area. So that's one thing that we should try here, is to say what happens when series are always positive. And so as with integrals, okay, establishing convergence is often simpler if we have positive terms. Positive or, I guess, non-negative. Having terms equal to 0 doesn't hurt anything. Okay, so one result we have, this is really analogous to a little theorem we wrote down for integrals. It's kind of almost the same theorem. Okay, so suppose that if an is bigger than or equal to 0 for some n bigger than or equal to k. So all this is saying is that maybe the first term is negative, and maybe the second term is negative, and maybe the 10th term is negative. But eventually there comes some point where beyond that the terms are positive, right? It's not a big deal what happens for the first few terms, right, if they're negative or not. What really happens is the bulk of the terms. So we start from here and go to infinity. Does that converge? Great. Then we can add on the first 10 terms, and it'll still be a finite number, right? So that's something to keep in mind. Just like with sequences, we kind of never really care what happens with the first few terms. We care what happens once things get big enough. So as long as these terms eventually become positive and stay positive, we're in business here. Okay? Then we're going to say that this series converges if its partial sums are bounded. Okay? Otherwise, it diverges to infinity. Okay, we know in general partial sums being bounded is not good enough for convergence, right? We did this sum of -1 to the n. The partial sums bounced between -1 and 0, right? They were bounded. They never got bigger than 1 in magnitude, but the series didn't converge. What will save us here is if these terms are always non-negative. If they're always non-negative, then we're in business. Okay, so proof, this comes down to what we know about sequences. Okay, so if we choose m and n to be bigger than k, then the partial sums are going to satisfy Sm minus Sn equals, okay, so Sm, Sn have a whole bunch of terms in common, right? So when we subtract them, all that's left is the bigger terms that lived in here but didn't live in here. So an plus 1, an plus 2, all the way down to am. And what can I say about this? It's positive, right, or non-negative. This is always greater than or equal to 0. In other words, if m is bigger than n, then Sm is going to be bigger than Sn, right? That's nothing but saying these partial sums form a monotonic sequence, right? As you go along the sequence, the terms in the sequence grow. So that is Sn is monotonic. Okay, and we know that for monotonic sequences, right, the terms are always increasing. Then one of two things can happen. either they keep increasing up to infinity, or if it's bounded, eventually they're going to run into this bound and they can't increase anymore, and then they're going to converge to their supremum. So the partial sums converge if and only if they're bounded. So Sn is monotonic. It's a monotonic sequence, and thus converges if and only if it is bounded. This reasonable? Okay, so again, positive terms make life easier, right? And then you're just checking if things are bounded. The other reason I write down this result is not for this theorem itself, but it's going to help us prove another really useful theorem that you're going to really like, that you've seen before. And it's a theorem that's proved very helpful in the context of integrals. It's going to prove very powerful here in the context of series. Was that a hand or a stretch? Richard?
No.
A stretch, OK. OK, this is our good old comparison test, right? As we say, I have a series, and its terms are complicated, and I have no hope of adding this up, and I don't know what to do. Let me try to relate this to something simpler. So this is our comparison test. None of these tests that we're going to see are really going to be new to you, I think. Most of them you should have seen in calculus. We'll write them down a little bit more carefully than you might have seen in calculus. Nuance some of the details a little bit. But they're the same tests. We're just going to see why they work now. So we're in the context, again, just like when we did this for the integral test, with positive or at least non-negative terms. Okay? So all of these things are non-negative, and they're ordered. So the ANs are always less than or equal to the BNs, at least as long as you start far enough along the series. Again, if this breaks for A1, order flips for A1 and B1, I don't care. If it flips for A2 and B2, I don't care. But at some point, these things have to get themselves in order and stay in order. Okay, so then what does our comparison test say? It says the same thing that it did for the integral test, right? If we add up these bigger terms and they converge, so Bn converges, then automatically An converges. And if we add up the smaller terms and it blows up on us, right? So if this sum diverges to infinity, then the bigger sum is also going to be forced to diverge to infinity. I'll write it the same way, equals infinity. It matters whether it goes to negative infinity. So in this case, they're actually positive terms. They're not going to go to negative infinity, right? Its only possibility is that they either converge to something finite, or the terms keep adding up and growing and growing and growing to positive infinity. Those are the only two things that can happen. But it matters that these terms are non-negative. This test doesn't work otherwise. So if we want to prove this, what are we going to say? We're going to say, let's suppose I'm going to do the proof of part A. Let's suppose that Bn converges. OK, we've got a series with positive terms, that means its partial sums are bounded. Okay, so then its partial sums are bounded. Okay, so in other words, there exists some number such that if we sum these things up, so let's say we take Bn and add it up from k to, say, m, this is always going to be less than c. Okay? For all possible choices of m. We'll say for all m bigger than k, I guess. Okay, so we start at k. We start at the point where we know the terms are positive. Add up as many of the terms as you like. I don't care how many, right? You can add up 1. You can add up 20 million. I don't care. However many you add up, this sum is going to stay less than c. Then we say, well, all of these terms are bigger than all of these terms. We're only adding up finitely many of them, right? So if we're adding up finitely many terms and we replace each of those terms with something smaller, we're going to get a smaller result. So move over here. We can hopefully see. So that means that also n equals k to m of all of my ANs, right, are going to be, okay, I replace them with something bigger and get a bigger result. And this is still less than c. So what does that say? It says this here, now I'm looking at these partial sums of my a's, right? It's partial sums because I'm starting at the beginning. I'm adding up however many terms you want. Could be 1, could be 10 billion, I don't care, right? No matter how many of these I do, no matter how far along I go in my sequence of partial sums, I stay less than c. So we're going to say partial sums of a are also bounded. Yes?
Does it matter that we only show that the partial sum starting at k?
It does not matter that we only show the partial sums starting at k. Because what you can do after that is say, let's take all the partial sums, add up the first k minus 1. That's just finitely many. It's fixed. K is a fixed number. It's not changing, right? So that's just a number. Add that number to this side, add that number to this side, and you've still got the same bound. Yeah. Or you could add up the absolute value of them. Yeah. Yeah.
Would it be safe to assume that since the initial value of an is already bounded between 0 and the value of bn, that
then it's fine. If the initial value is already bounded between 0 and bn, then it's fine. Yeah. And that's the case you're going to see a lot of the time. So these are bounded. The ANs are all positive, right? So since AN is bigger than or equal to 0, we must have that. Therefore, actually this series converges. Because we said a series of positive terms that has bounded partial sums, automatically convergent. Okay, part B, I won't write out part B. Part B is very similar. right? You show that the partial sums of an are unbounded, and therefore the partial sums of bn are unbounded, and therefore we diverge to infinity. So similar, it should be in the book, and I just said it in words. Okay, so for example, we can take this series, 1 over n plus 1 squared. Okay, this shares a certain similarity with the series we've already been looking at, right? We've looked at in a couple different ways at 1 over n plus 1. That series was simple because we could write it in a way where things, or neighboring terms kept canceling, and it was very easy to work with. This is going to be harder to write in a way where you get simple cancellation. So we've got to see what we can compare it to. So one thing we can notice is that certainly these terms are all positive. I also know that I could make this bigger by making the denominator smaller, right? So if I say, let me take one of these n plus 1s and decrease it a little bit, since it's sitting in the denominator, decreasing it a little bit makes the whole thing goes up. So this is certainly less than 1 over n plus 1. Okay, this guy, right? Again, this guy we've already looked at in a couple different ways. He was pretty easy to work with because we had beautiful cancellation happening. The same tricks would not be so easy to apply here. But we've got a really simple test that says I can use all the old work that I've already done. We already saw. So we saw that this guy converges. And we're done. We're in business. Just by comparing the terms, we know straight away that the series we're really interested in also is going to converge. Okay, so that's your trick in general. Is you take a series, you say, it looks complicated. What does it have in common with a series I already know something about, or a series that I could analyze pretty easily, right? How does it relate to that? You try to relate it to that. And secondly, this is important, right? It's important these things have a sign. If they don't have a sign, this trick doesn't work. Hey, we could do another example. This guy, n times r to the n, where r is some number bigger than 1. Okay, there's different ways you can analyze this one. One way would involve the comparison test, or we'd say, well, this looks pretty similar to a geometric series, but there's an extra little bit in there. So we can look at this and say, well, we know that 0 is less than r to the n, is less than what happens when we multiply by a number that's bigger than 1. And it's going to diverge to infinity. So we look at this, we say, this is a geometric series. Diverges to infinity. Okay, these are geometric series. That means we have formulas for the partial sums, and we can figure out exactly what happens to them as n goes to infinity. And in this case, since r is bigger than 1, it diverges. So then right away we say, well, by the comparison test, since the smaller sum diverges to infinity, the bigger sum has got to go along with it. Any questions on the comparison test in general, or these examples? Right. You've used the comparison test before, right? Maybe it's rusty, that's okay. But I know you've used it before. It's nice to see now, where does this thing come from? And hopefully you believe now that your calculus professors were not lying to you when they taught you this. Okay, we're playing with integrals. So all this was kind of motivated by what we've already learned from integrals. And again, we've seen before there's a good relationship between integrals and series. And in fact, we did an example with an integral where we were trying to figure out if it converged, and we related it back to a series. That means maybe that's a trick we can use in general, that we can take series, relate them to integrals, use what we know about integrals. Okay, this is our integral test. Okay, we're going to say let's let f of x be a positive, non-increasing function. And if we're going to relate this to integrals, it better be locally integrable. Okay, and I want to define for x bigger than or equal to 1. I don't care what it does when x is less than 1. Okay, then this theorem says there's a great correlation between adding up discrete terms of f or just integrating f. And in fact, this series converges if and only if the integral from 1 to infinity converges. Right? So you can use this two ways. I give you an integral and say, does this converge? You say, it's kind of hard integral to do by hand. But if I just look at discrete terms and add them up, maybe I have some tricks I can use to decide that that series converges. That tells me something. Or you can say this series is kind of hard to work with, but I would know how to integrate this function. I can use what I know about the integral to decide if the series converges. So this works both ways. Yeah?
In the left-hand side where we have the sum from 1 to infinity,
yes.
Could you replace n
by something bigger?
In f of n by some monotonic increasing unbounded sequence?
Could you replace n in here by some monotonic increasing unbounded sequence?
Like Sn.
You would have to do that delicately, I guess. Right? You'd have to make sure that the substitution also works through here, because you may be adding weight where you don't want to.
Good. Yeah. So if you added like a very simple sequence like 1/10, 2/10, 3/10, I assume this would probably also.
This would probably go through, yeah. But you'd have to pass the substitution through here. So what I would actually probably do in that case is just take your substitution and do the substitution right here, so that's rewritten in terms of n equals 1 to infinity of f of s of n. And then I say, can I integrate f of s of x, for example, right? So you can still use the test.
Cool.
All right, so why does this work? All right, we know there's two parts to this proof, because it's an if and only if. I don't think I'm going to do both parts for you. I'll do one part, and the other part is very similar. But of course, it's worth remembering there are two parts that need to be done. So part one, I'm going to assume that the series converges. Okay, so series converges. We happen, again, to be in the situation where we have a positive function here, right? We're working with positive terms. Life is easier when we work with positive terms. So if we know that this series converges and we know that the terms are positive, what else do we know about it? Yep?
Partial sums are bounded.
The partial sums are bounded. Okay, so this means since f is positive, the partial sums are going to be bounded. Okay, so in other words, there exists some real number such that if I look at these partial sums, if I add up the first n terms, I get something less than c, no matter how big I take n. Okay, we need to relate this back to the integral. We've made arguments like this before with integrals, right? Where we say we have a function that's positive. We do something analogous to the partial sums, which is that we integrate up to a point, but we stop eventually, right? We don't integrate all the way to infinity. We just integrate part way, and then we stop. And we've written this kind of function down before, so I'm going to write it down again. So capital F of x is that we integrate from 1 to x. Okay, again, this is a positive function, right? We're looking at an improper integral. We want to know what happens as we take x to infinity. But we know that since this is a positive function, all we need to do is show that this guy stays bounded, right? Pick any x that you like. This number has a bound that doesn't depend on x. And we've got kind of a reasonable candidate for a bound over here. So this is going to be our goal. Show that f, capital F, is bounded for x belonging to 1 to infinity. And the real goal is, can we show that f inherits the bound c that comes from these partial sums? Okay, so capital F of x. I need to work with inequalities that go this direction. I'm trying to show it's bounded above. So again, I don't need to show f of x is exactly equal to something. I just needed to get a bound. I know that I want to try to get back to something that looks like it goes from k equals 1 to n, something that looks like this series. So it starts at 1 and ends at an integer. So this is actually sort of relevant to your question before. Does n star have to be an integer? No, in general, I don't care. But right now, I do care because I'm trying to get back to something that I can write as a series. And this series is only allowed to involve integers. So what I'm going to do is take this x, and I'm going to round it up. Right? So before I was integrating from 1 to x. Now I'm going to integrate from 1 to something a little bigger than x. And that's going to make the value of the integral go up because we're integrating something positive. Okay, so this, I can write it actually in this way. I'll do it in two pieces. So this was my original capital F of x plus whatever I get when I integrate from x to whatever is the next integer above it. Do you know this notation? This is the ceiling function. So it just means I'm taking my number and rounding up. Okay, this, in other words, is the integral from 1 to the ceiling of x. Okay, and now we're going to do a trick that we've actually seen before. We know we want to take this, and we want to turn it into a series. So the easiest way to start turning it into a series is to say, let's integrate from 1 to 2. Then let's integrate from 2 to 3, from 3 to 4, and so on. And just split up my integral like this into little pieces, right? We know this. We know this about integrals. We can break them up. Do the whole thing at once, or do little pieces and add them up. Right? And that's all fine. Again, this guy is locally integrable. There's no big deal integrating him on this. This is perfectly well defined. But I want something that looks like a series. So let's try to write it like a series. We're going to take our series where n goes from, or let's call it k goes from 1 to ceiling of x minus 1. And I'm just going to integrate from k to k plus 1. So I'll integrate from 1 to 2, from 2 to 3. And eventually I get here and I'll integrate from x minus 1 to x. So we're going to integrate from k to k plus 1 of f of t dt. And I haven't lost anything here, right? This isn't exactly equal. This is an equal to sign. It's not an inequality. All I've done is break up my integral. And the reason I broke up my integral is because I know I need to make this look like a series somehow. But again, it's not important that I have equal signs running through here. I need inequalities. And I need to be able to make this integral go away, right? I'm allowed to, what I would like to have here is an f of k, because we know that we're trying to look at partial sums of these f's. So how can I do that? I can say, well, this is a positive function. We're doing an integral. We have comparison results for integrals. So we know that on the interval, so for, let's call it t, for t belonging to k plus 1, what's going to happen here? Yeah.
We can take f of k plus 1, which will be the supremum of that.
So we can take f of k plus 1. So let's just think about this a second. I'm trying to make the inequality go this direction. Which side is, what do we know about the function f? It's decreasing, right?
Okay.
Right. We better not be integrating an increasing function. We're in trouble. So f is decreasing or not increasing, right? So that means it's going to be biggest on the left-hand side. And then as we go to here, it goes down. So on this interval, we're going to have f of t always less than or equal to f of k, since f is non-increasing. F is going down. That lets me do this trick. So again, that's an important piece of this test. When you do the integral test, it's going to matter that we have a function that's going down. Otherwise, the integral test isn't valid, because otherwise this step is not valid. So we're going to have f of t less than or equal to f of k. And since those things are both positive, I can use my comparison test. So not only is that true, they're both positive. So I can do comparison on all of these little integrals. And I can say, I'll get something bigger if I integrate f of k. So this was one of our comparison results for integrals. Right? So here, it was a comparison result for just a standard integral, perfectly well behaved. And here, this is just a finite sum. I'm not playing with infinite sums. Well, as soon as you're playing with infinitely number of terms, you have to be really careful with the tests that you use. But this is just finitely many terms. So it's no big deal. We know how to add up finitely many numbers. This is good. Now I can integrate this exactly because this is a constant. Right? So this is now constant. It doesn't depend on t. So I can work out this integral. It's nothing but f of k times k plus 1 minus k. Okay, so this is the sum of the first several f of k's. And this should look familiar. What are these? It's almost the original series. It's the partial sums of the original series. So these are my partial sums. Right? Now we started out by saying we know these partial sums are bounded by c. This is always less than or equal to c, and it doesn't matter what x is. Right? Doesn't matter how big this number is. These are always less than or equal to c. So I'm going to say this is true for all x, no matter how big. This is exactly what we wanted, right? We wrote down this capital F. We said we're integrating a positive function. That means as long as we can show that this capital F has a bound, bounded above, we're in business. We know that the integral converges. That was one of our results from improper integrals. So since capital F is bounded, and again, F was non-negative, we can conclude that this integral converges. And that's exactly what we wanted to show. We started by assuming the series converged. We said if the series converges, automatically the integral converges. Okay, so part 2, we would assume that this converges. And we would show that. If that happens, automatically our series converges. Okay, I'm going to use similar arguments for that, and I'm going to refer you to the book for the full details. Any questions on that? That's our integral test. It's a nice result. It's obviously a useful result. I mean, you've seen it before in calculus. And it's great because we have a lot of tricks that we know for integrals. And now all those tricks automatically give us a whole bunch of tricks for learning about infinite series. You know, we're one big result, and then we can do a whole lot without much work. But make sure, again, make sure if you're going to use the integral test that you verify the hypothesis. You better have a function that is positive. You better have a function that is not increasing. It's going down, right? Those things have to be true, or these steps don't work.